Okay, radiative transfer equation. So we're going to go through a lot of these things, all these things. And we'll start with a little bit of setting the scene for thinking about the radiative transfer equation and deriving the radiative transfer equation. So we have some body of water. It's described by its inherent optical properties, so think about absorption, scattering processes. And what Andrew showed you nicely quite near the start of his lecture was these inherent optical properties are affecting the light field in some way. They're affecting the radiance and the irradiance. And so the relationship between these two different things is described by the radiative transfer equation. And so the propagation of light in any absorbing, scattering material is governed by the radiative transfer equation. And so this is something that you can think about in the atmosphere, it can be in the water. And that's kind of actually where the move for thinking about radiative transfer in the ocean came from. People moved that knowledge from the atmosphere. I said that, great. And so what we're going to do today when we're thinking about deriving the radiative transfer equation, and I don't know if you all think back, way back to a week ago, to Patrick's first lecture, you actually did a very quick derivation of the radiative transfer equation. And we're basically just going to redo that, but you've learned a lot in that past week. And so hopefully some of that will kind of click together a bit more. And so we're going to be thinking about how radiance changes along this path, this kind of lighter block here. And so the path of that beam is going to be described by a vector r. So that's some x, y, z direction. And this r is at this angle theta to the z direction. So we're thinking about radiance. And so Andrew was just talking about this. What is radiance? Remember the difference between radiance versus irradiance? Okay, so radiance is the one that's measured how?
Gershon tube.
Exactly, Gershon tube. Yes, right. This one's actually pointing in the wrong direction for the direction we're thinking about. But the radiance is this flux in a given direction, thinking about per unit solid angle per unit area. Okay, this is all we need to know for deriving the radiative transfer equation. So we're just going to go. So we have our light beam, and we're going to be talking, it has some radiance, and we're going to be thinking about how this radiance changes along the light path. So if we're talking about change in a mathematical sense, how would you describe that mathematically?
Using derivatives.
Exactly. And so we're talking about the change in radiance along our path R. So change with respect to the path. Okay. And so if we think about what processes are going to affect the radiance. Okay, I have 6 processes written down. Can you figure out what all those processes are? So you've got your light, it's interacting with water. What processes are going to affect it? Scattering, absorption. Scattering in what sense? I have 4 different scatterings here.
Reflection, refraction.
No, I'm thinking about so
Scattering in, scattering out.
yeah, scattering in and scattering out at the same wavelength.
Scattering in and scattering out. That's just
Scattering in and out in different wavelengths. And then the final one, that was 5, is emission. So just emission along that path will happen. Okay, so we're going to start with absorption. And so that, if you think about it, is loss of energy along that beam path. So my arrow gets a little thinner. Like that's obvious. And actually, the term that we use to describe this loss is just the absorption coefficient times the original radiance that was going in. Not too complicated. And then we think about scattering out of the beam at the same wavelength. So this is another loss of energy out of that path. And it's actually similar to this absorption term. And so the amount of loss is just the scattering coefficient, again, times by that radiance. And then, this is where things start to get a bit more complicated. The scattering coming from the gain of energy into the beam, and we're thinking about here at the same wavelength. So, I'm removing all that other stuff just to kind of clear up the screen for a bit. So if we take a step back and think about the volume scattering function, and so this can be described as the scattering intensity per unit incident irradiance per unit volume. So what we're saying is, we can't see my mouse. So like if we're thinking like at this point here, you have this beam, this light coming in from a different theta and phi, just given a prime notation to denote a different direction. And so the volume scattering here is this scattered intensity per unit incident irradiance. And so this is the irradiance that's been coming in. And we're talking about the intensity along the beam. So you note the difference in the angles here, per unit volume. Okay. I'm not sure if you saw this explicitly in earlier lectures when you talked about the VSF, but this is a different way of defining the VSF. And then if we think about some of these terms that we were just learning about, the irradiance is the radiance times all the possible different angles. So if you think you have your Gaussian tube and say you're like looking down at this point, if you looked at that point from all possible angles and added them up or integrated them, that's how you get to your irradiance from your radiance. So it's this one plus this one plus this one plus this one plus this one. And so that's what this equation is telling us. Okay? Everyone following? Do you want to take a pause? Ask any questions? Keep going? Great. So the scattered intensity is then that radiance times the unit area that path is going through. So like we're thinking about this as a volume, but you can also think of this having a cross-sectional area. And so it's that the intensity can be described as then it's radiance along the path times the area that light is going through. And so if we put all this together, we end up with this. So I've done a little bit of rearranging. So we have our scattered intensity is this term over here. And so then we have times our volume scattering function times our incident irradiance, which is our incident radiance times the volume. Okay. And then if we see here, we have this volume and area terms. These cancel out with each other to give us our path, our distance along our path. So our cross-sectional area times the length of our path will give us our full volume. And so we're simplifying this so that everything is written now in terms of R. Because, and this, we're just clearing up slightly. And so now we have this thing in terms of a delta R, and this thing in terms of a delta omega. So omega is our solid angle. And so we can actually integrate this over our solid angle. And that's what we're doing as we move from here to here. And we're going to expand this out a little bit and explicitly write this out in terms of integrations in terms of your theta prime and phi prime rather than an integration over the solid angle. Okay. And that is how we're leaving it for this scattering gain. Yes.
So initially you just represented that incident light ray with R lambda theta phi.
Mhm.
But then kind of in this bottom left, you add that delta A term. So through that delta A, are you just doing a energy balance? Is that what?
Yeah, this delta A term comes into it when we think about the scattering intensity here. And so that's where the delta A term comes into it. If that makes sense. So we are kind of ignoring this incoming beam for the moment, and we're just thinking about the VSF, and that the VSF is described by the scattering intensity divided by the irradiance per unit volume. And then the scattering intensity along the beam path is related to the radiance times the area. So it's slightly decoupled from what you're thinking.
Gotcha. And that's R plus delta. That's the difference.
Yeah, exactly.
Okay.
This is R plus delta R. So it's like as we move along this path. And so like you can see that this is actually a derivative term too, which makes sense because as we started, we were talking about change along the path. So it's a derivative too. Okay. So if we put this in, we now have this. So far we've got our change in our radiance is going to be related to this absorption term, this scattering loss term, and this scattering gain term. Okay. And so now we're going to think about inelastic scattering. So loss along the beam with a change in wavelength. And so what's the process of inelastic scattering? Someone describe that to me. What happens?
Absorption wavelengths, radiation at another.
Exactly. So you're absorbing a photon at one wavelength, emitting it at a different one. So if when we're thinking about this equation and we're considering a wavelength lambda 1, and we're thinking about there's been some regular absorption at that wavelength, and then you've got some absorption that is actually from inelastic scattering, mathematically, they're the same thing because we're only looking at that one wavelength. And so we don't care how that photon was absorbed and what happened to it afterwards. All we know is there was a photon absorbed. The emission of that photon at the different wavelength, the inelastic scattering part, comes into the equation in a different place. So we actually don't need to add anything for inelastic scattering for loss of energy. It's bundled into this absorption term already. Which actually brings us to the final term. And so this is, I just gave the game away a little bit. So now we're talking about the gain of energy along the beam with the change in wavelength. And so that's this is the second part of almost what we just talked about. You can kind of think of it in that way or in a slightly different way. But the point is we are getting energy at some wavelength. And there's another process, the other process that I talked about, just regular emission. So this is a process, something like bioluminescence, where we're gaining energy at a wavelength. So in the same way that we bundled absorption and loss because of inelastic scattering, we can bundle gain from emission with gain from inelastic scattering when we're considering a given wavelength, if that's the wavelength those processes are happening at. But these processes, there's actually a bunch of different things, different ways and different processes that photons can be emitted by or inelastic scattered by. So fluorescence due to chlorophyll or fluorescence due to CDOM or bioluminescence. And each of these different processes actually requires a separate mathematical description to describe that gain of radiance along the path. And so normally when we represent the radiative transfer equation, we just use a generic source function that we just call S. And so then something explicit is added depending on which process it is that you're interested in. And I actually have no idea what the form of those source functions are because I've never considered them when I've been doing any work for the radiative transfer equation. But I'm sure we could probably find some somewhere. Okay, so this is it all. And if we just piece all these pieces together, we have the change in radiance along the path is the loss from absorption and scattering for the radiance, our source term, and then this big crazy integral. And so this is it. This is the radiative transfer equation for changes along the beam path. Okay? Great. It looks very complicated, and unfortunately it is very complicated when it comes to trying to solve it. But first we're going to think about it in a slightly different way. So here we've been talking about, we derived it and thinking about it in terms of light along the path, but normally in the ocean or in a lake or in your water aquatic environments, we think about things in terms of geometric depth in the water column. And so most of us in the ocean optics realm are more familiar with seeing this written in terms of Z, in terms of depth, rather than in terms of path. And so if we do a little bit of trigonometry, our cos theta is our Z divided by R, or R is Z cos theta. And so if we substitute this into this equation, and this A plus B is equal to your attenuation. That just simplifies that slightly. We have a slightly different form of the radiative transfer equation. And this is kind of what I'm more familiar with seeing. And so we have this cos theta dz term from that dr, and then you see everything else is just represented in terms of depth. Otherwise, exactly as it was before. Okay. So we only have one slide on solving the radiative transfer equation. So here's our great equation. So it's very difficult. But like if you look at the radiance terms in this equation, right, what do you notice? We have radiance written 3 times. One it's a derivative, one it's itself, and one it's an integral. And the derivative and the integral are on opposite sides of the equal sign. So even if you thought about how you might try and pull out that radiance, if you try to integrate to get rid of the differential, you end up with an extra integral on this side, vice versa. And so it's really hard to have a fully analytical solution. So we only get exact analytical solutions for very simplified versions of this equation. And we're going to talk about a couple of approximations just coming up. And so you can get these approximate analytical solutions for a couple of things. And these both of these involve like some kind of assumptions that we're making about the environment that we're in to make it easier for us to solve this equation. And so there's a bit of uncertainty then in the radiances that we get out of that. And so the most accurate solutions are actually done using numerical methods. And for a long time, Monte Carlo methods were kind of the most widely and more commonly used. But there's also something called hydrolite. People heard of hydrolite? I don't know if you talked about installing it, but we're doing a lab with hydrolite this afternoon. And so it's a numerical radiative transfer software. It was written by Kurt Mobley, and it uses this invariant embedding method, which I don't really know anything about, but as there a copy of Kurt's book floating around, Light and Water. There's a whole big section in that book that I've never read, but it basically describes how hydrolite works and how to solve the radiative transfer equation using these numerical solutions. But But now I would say a kind of a mix of both of these methods are used. Because it can be really useful to do some of these modeling exercises to think about, like, here I have a bunch of IOPs. What does that mean the underwater light field is? And does that match to what I measured with my radiometers in the water as well? And so we're going to talk about first the quasi-single scattering approximation and then Gerson's law, where we're going to actually derive Gerson's law, which Andrew showed us earlier. And so this approximation is that there's no scattering in the forward direction. So already you could be like, okay, that's a big approximation, potentially. But if we think about it, in ocean waters, we typically have like quite forward peaked phase functions. So the scattering is at small angles. So a lot of forward scattering. The scattering is all at like these small angles. And you can assume if you're only scattering at a tiny amount, you're not really scattering at all, right? It's the same thing. And so that's basically what the assumption is. And so mathematically, we in this approximation, we talk about the forward scattering part of the phase function being approximated by a Dirac delta function at that angle of 0. Are you familiar with the Dirac delta function? And so we're basically saying here, we have theta equals 0, and we have all our scattering like that, i.e. no scattering. Okay, so if you make this assumption, then some of these, I'm not sure you've necessarily seen all of these, but some of these kind of common parameters we use simplify. Your attenuation, which is your absorption plus your scattering. If you pull that scattering apart into forward scattering and backward scattering, then you just have your attenuation becomes your absorption plus your backward scattering, because there's no forward scattering. Similarly, your single scattering albedo, which is normally scattering divided by attenuation, becomes BB over A plus BB. And this may look familiar to some people, may give a hint of where we're trying to go with this. And then as well, sometimes we think about things in terms of optical depth rather than geometric depth, where the optical depth is beam C times the geometric depth. And so again, this becomes A plus BB times your geometric depth. And then there's something called just the single scattering approximation of the radiative transfer equation. And we're not going into the maths here. It's kind of complicated, but it is all on the Ocean Optics webbook online if you're interested. But that assumption or approximation results in this equation, which basically, we have our single scattering albedo, we have our irradiance, we have a volume scattering function described by various angles. It's fine. We don't really need to worry about this too much. Yes. So
what letter called under optical depth?
Zeta, I think.
Oh,
It's
yeah.
Zeta. Zeta. Anyone up on the Greek alphabet? I think it's a zeta. You don't think it's zeta? No? Well, someone back there can Google it for us.
It's a zeta.
This is zeta. Great. And these are actually mu's rather than thetas. And this relates kind of to thinking about like that cosine angle. And so a mu is cos theta. And it's just a different way. Zeta. It's my accent. That's it. It's throwing everyone off. But anyway, this is what the single scattering approximation is. And so what if we substitute some of these assumptions into it, namely here, we get this BB over A plus BB. And have we learned about remote sensing reflectance yet? So that's it. This is going to be the first time. So remote sensing reflectance is, you're going to learn more about remote sensing reflectance. But remote sensing reflectance is described by the the upwelling radiance divided by the downwelling irradiance. So if we pull this part out, what we end up with is this equation, which is BB over A plus BB times something that's kind of related to angle in geometry. We don't really care about that. And so simplifying all that something down into one nice big letter G, we end up with this remote sensing reflectance is equal to something times the backscattering divided by the absorption plus backscattering. Has anyone seen anything that looks kind of like this before? Yeah, so some of you are nodding. And so this is an approximation that is used quite a lot in the remote sensing world. And actually, you may have seen it with an additional term with this squared on it as well, which actually comes from, we talked about this single scattering approximation. But if you take the next term as well, so think about like 2 levels of scattering, and that's where that BB plus A plus BB squared comes in. But the point is here, like this G, there's papers in the literature that have derived, numerically derived, like a value to represent that G by. So using things like hydrolite, where they put in a bunch of different geometries and then look at the relationship between those IOPs and the remote sensing reflectance. So then you can use this approximation to get a sense of what your remote sensing reflectance is if you've just measured IOPs. Or vice versa, if you've measured LU and ED in situ and you've measured your backscattering and your absorptions, you can try and match these to each other to get a sense of all your measurements are good quality, because they should behave really nicely if you plotted your RRS versus your BB over A plus BB. And I'll actually show you an example of that slightly in the lab later. Yes. G is just me calling this thing G. Oversimplification to make the equation easier to read.
So just to understand, the 0 is the depth.
Yes,
And-
sorry, yes. 0, we're at the surface. Yeah.
And the mu is combining our data and our wavelength, or are we assuming invariance to wavelength?
At this point, we're assuming invariance to wavelength. Like you could put a wavelength in this, and so it holds for every wavelength. But yes,
But
the mu is cos theta, because we're thinking about it in a slightly different geometry, I guess, in this sense.
But G is not the same at each wavelength. It's just that this is
G
standard.
is the same, actually, at each wavelength. That's a good question. But yes, they use G at the same wavelength. And there's actually another approximation people may have seen where it's just BB over A, and it doesn't have this term. You can actually derive that in a different way. Or the other way people think about it is if it's not a very scattering situation and absorption is dominating on this nominator, then the absorption just dominates, and so we don't have that A term. And so that's another approximation that's used sometimes, you may have seen. Okay. That's that part. And then the final part, Gerson's law. So say we decide, so here we're dropping wavelength again, just to save writing out wavelength every time. And say we decide we want to integrate this equation. Okay, just cause, why not? So if we integrate this term, so we're integrating it over all directions, so over all solid, over a solid angle. And so what this is, this is just a rearranging and pulling the derivative out to the front. And then this term over on the end is equal to the derivative of ED minus EU. And so if we think about this, our ED is our radiance integrated over, see, this is a whole hemisphere, and this is the full sphere. And so normally your ED would be integrated over, well, ED 0 to pi by 2. Is it that way? I guess it depends your coordinate system. And 0 to pi by 2, whereas your EU would then be pi by 2 pi. And so here we're going over the 0 all the way to pi. And so it results, this integral is the difference between the two. Okay? Well, confusing, but it is. So that's that first term. If you integrate that, that is your result. And then if we look at this next term and we integrate it, we can pull the c out to the front of our integral. And then you end up with this term, which I don't know if we looked at that expression explicitly, but this is our radiance integrated over all possible angles, which is our scalar irradiance. Okay, so we're beginning to see some things hopefully coming together. And then this final term, fortunately, a bit more complicated, integrating it. We have a bunch of different angles, integrals with respect to different parts. And so we're pulling these two different parts, you know, as into separate integrals. So the integral with respect to this set of solid angles and the integral with respect to this set of solid angles. And so then this is actually like we just had here. We just had phi's on all our angles, but it's the same physical property. So this is another scalar irradiance. And then this is your scattering coefficient. So this really complicated term cancels down to being your scattering coefficient times your scalar irradiance. So what we have is our derivative of the difference between ED and EU is our minus C plus B, both times the scalar irradiance, which is minus A. And so this, as Andrew talked about quite a bit, this is relating our absorption to the irradiance and these three different measurements of the irradiance. And so this can be a really useful property like we talked about. How if you're measuring irradiance at these three different irradiances, you can actually get an estimate of absorption. Okay, great. And that's it, honestly. There's a lot of math in there, so we're not going tons, but just to summarize like what we did do. So the radiative transfer equation describes how radiance is changing along the path. There are 6 processes that are governing that: the absorption, elastic scattering into and out of the beam, inelastic scattering into and out of the beam, and then emission along that path as well. And so there's a bunch of different analytical approximations and the numerical methods are needed to solve the radiative transfer equation. And then we just looked at 2 of these approximations. One leads to this quite commonly used relationship that RRS is proportional to your BB over A plus BB. And the other one is Gerson's law, which relates absorption to irradiance. And that is all I have for you for this lecture. So if you have any other questions, yes.
With Gerson's law,